Okay, in this video lesson, we're going to start our next unit on thermochemistry. Thermochemistry unit, we're actually going to break it down into 3 different modules. So instead of doing one big unit test at the end of the big unit, we're actually going to do 3 kind of smaller mini tests as we go through to help focus our studying and to help us deal with the large quantity of information in thermochemistry. So here we go. First of all, if we're going to do thermochemistry, we really need to know what energy is. So talking about energy, hopefully it's not the first time you've heard about energy. If we were to define it, we would call it the ability to do work or cause change. Now that's pretty vague, I get that. But really, if you think about energy, is anytime that we are creating movement or causing changes, you're expending energy. So that really is a pretty good definition for it. I like to think that energy is kind of like the opposite of mass, where mass is a physical thing that we can put our hands on, but energy is more like the verb or how things move and change, where mass is more like the noun. Okay. The unit of measure we use for energy is the joule. It is capitalized, so please use a capital J when you use the symbolism for joules. And then we get a joule because joules come from the energy that it takes to produce 1 watt, which you may have heard from light bulbs, for 1 second. Okay. Now that might be pretty vague to you. So one idea is like, how do you figure out what joules are? Well, a single green pea. So think of like one pea of food has about 1,000 joules of energy in it. Okay. That's tiny. Okay. So joules are extremely small. They're tiny. So often we don't use joules. Instead, we often use kilojoules because they're a more usable measure for us. Okay. Now that's only about 1/4 of a food calorie, to give you an idea how small that is. Calories are interesting too, because calories, as you read calories on the back of a food label, they actually use a capital C to represent that, which is actually a kilocalorie. So in the science world, 1 calorie equals 4.18 joules. That's our relationship between those two things. But when you read a food label, if there's like 100 calories in something you're drinking, they're actually taking that times 1,000. So if there's 100 calories in there, there's actually 100,000 scientific calories, or what they're saying is that there's 100 kilocalories in the food. And they do that because basically I think they don't want to write things like 100,000, 200,000, 500,000 on labels. Okay, so they just use kilocalories. They don't say kilocalories, they use a capital C versus a lowercase c. It's a little trick that you have in the food industry. Just something to make note of. So as you deal with calories, you might see that also. Okay. Now, within the idea of energy, we should have a pretty good understanding, or maybe we've seen the terms before, of kinetic energy versus potential energy. And we'll use that in this unit also, okay? So a reminder that kinetic energy is anytime we have moving energy, and potential energy is anytime we store it, okay? So if we take a look at these different examples of places we can get energy from, like batteries, electricity, gasoline, a compressed spring, heat itself, a bonfire, a wound-up toy, candy bars, your earbuds playing music. If you take a look at these and we start to categorize them, so maybe take a minute, pause the video, and try to say, okay, which one goes where? So like a spinning wheel. Well, it's spinning, so it's probably kinetic. It's moving, okay? A compressed spring, well, it's compressed, but it's not moving, so it's probably just storing energy. So as soon as you unleash that compression, it would become kinetic, okay? That kind of stuff. So pause the video, try to figure out which one's which, and then start again. Okay, assuming you paused it, we'll just hit a button here and we'll rearrange them, and you can see that where they land. Did you get them all right? Did you not? Okay. Usually I find that some people like to put sunlight as stored energy, but the actual light itself is carrying energy. And sometimes people put batteries as moving energy, but the battery itself is actually a storage house for energy. Now, we could use that energy from the batteries to use our earbuds to play music, but the batteries themselves store the energy, okay? Of these, we're going to focus on a couple for chemistry, okay? So in chemistry, when we look at kinetic energy, we're really looking at that moving energy that acts as heat, okay? So our focus is going to be almost solely on heat energy and how heat energy works. Yes, light's important to us too. We see flashes of stuff, but it really is very minimal in comparison to the heat changes that we can experience in chemistry, okay? Now remember that when we have kinetic energy, we're going to measure that with temperature, okay? Because temperature can measure heat energy, but temperature doesn't measure total heat energy. It's just that average kinetic energy of our system. So when we measure temperatures, we're finding the average kinetic energy within that system. And we learned previously that at any time you have a system that you're going to have a range of speeds of particles. So there's going to be a range of different energies there. So that's why we need to have that average as we measure this. Now the potential energy that we talk about is going to be our stored energy as bond energy. Okay, this one might be kind of new to you. So bond energy is actually the energy that is stored in the chemical bonds themselves, okay? And that's kind of out there. So the actual chemical bonds that we have, those ionic bonds, those covalent bonds, even those intermolecular forces, that IMF that exist, that bond actually is a storage house of a small amount of energy. So each bond has a tiny bit of energy that it's storing for us, okay? And what's kind of cool is in the world of chemistry, we can actually unlock that energy from those bonds and use it if we want to. Or if we don't want the energy, we can actually lock it away and store it in chemical bonds. So it's almost like we can make chemical batteries out of our compounds and use it the way we want to, okay? So anytime you see that phrase bond energy, your brain should go to potential energy or stored energy inside the bonds, okay? And we do use the word bond here, but it can be IMF too, okay? Kind of talked about this already, but kind of one of the cool things in chemistry is that we can manipulate this. So we can convert kinetic to potential and potential back to kinetic, either storing it when we want and moving it when we want. Kind of cool. Now, that brings us to this idea of total energy of a system, okay? So because we can mess around with potential energy and kinetic energy, we can change those things, we need to remind ourselves that yes, we can increase kinetic and decrease potential or vice versa, but the total energy should stay the same. So for example, right now we see that we have kinetic and potential energy very similar to each other. But if kinetic energy were to go up somehow in our system, that would mean potential energy would have to be decreased by the same amount. So it is an inverse proportionality here. Notice how our total energy does not change at all. Okay, exact opposite can happen too. So if the kinetic energy gets reduced, we could store things as potential, but that total energy stays the same. Okay, hopefully you are seeing that we're going to go down the road into basically the law of conservation of energy, which we've talked about law of conservation of mass. So it's good to bring in the law of conservation of energy here also, which basically tells us that in any chemical or physical process, the total energy cannot be created or destroyed, okay? So as long as we keep track of energy, we should be able to account for it at all places. Reminder, even though we talked about this earlier this year, reminder that mass does not turn into energy and energy does not turn into mass in a chemical or physical process. It's really common that people think like burning a log, the mass is what makes the energy from that. Or when you burn a candle or the gasoline, because in combustion reactions, we see these heavy logs or these gallons of gasoline, and then afterwards we see nothing, so we think that the mass is converted into energy. Completely false, not true. If you recall, combustion reactions make carbon dioxide gas and water as a vapor. So we're still conserving that mass, but that mass leaves as vapors or gases and we don't see it, okay? But you might say, well, Mr. Dirksen, you get a ton of energy out of burning a log of wood or burning gasoline. Yeah, we do. We get a lot of kinetic energy out of it. We get a lot of usable heat energy. Well, where was it originally? Well, it was stored in those bonds, okay? So what people don't realize is gasoline actually, its chemical bonds actually stores a pretty decent amount of energy for us. Most of our petroleum products or fossil fuels do, and that's why they're a good source of energy for us. Okay. Same thing for wood. It stores energy in its bonds. So then when we react it, combust it, we actually convert it from potential to kinetic, and we use it as kinetic energy. So we are just moving energy around. All right. So if you ever think that energy is gained or lost, it's not true. Okay. You're probably just not tracking where it all is either coming from or where it's all going. And that's going to be one of our goals in this unit, is to make sure we track that as we kind of go through. Okay. So that brings us to this idea of what does chemistry really do on like more of a broad scale, okay? So what we're really doing in most of our chemical reactions is we're causing a shift in kinetic or potential energy, okay? So we are rearranging chemical bonds, or IMF. Okay, IMF is part of this because we can actually move energy around by changing IMF too, okay? And that's what we do in chemistry. All right. Well, that's why things get hot. That's why things get cold. That's why light flashes away. That's why we feel energy coming off, or we see it absorbing in. That's what happens. Okay. So there's two results from that. We either have the scenario where the new bonds or the bonds of the new compounds, whatever we're forming, creating, whatever we're doing, they need to store more energy than the original ones, okay? So the process requires more energy to be stored, okay? Well, when that happens, the potential energy is going to need more, so it's going to steal it, or the kinetic is going to convert into potential, okay? Remember how they can convert back and forth? So this is one scenario that happens. Okay? We'll actually give a name for this in our next couple of slides. Or the other way around. The new bonds from those compounds, they need less, okay? So they're going to store less energy. The old ones had more, so if you're going to store less, you need to get rid of your excess, okay? So if you start with a whole bunch of potential energy and you need less at the end, then your kinetic energy is going to increase or be converted because you're not storing as much from before, okay?